In addition to exceeding a control limit, the occurrence of a trend, run, or middle third also indicates an out-of-control process. These will be discussed in this lesson. And hello again to this lesson, which essentially has 3 learning objectives. What you see here is a value curve in a quality control chart with its lower and upper control limits. These are placed in such a way that the probability of exceeding these limits is less than 1%. After this training, you should be able to assess the probability of occurrence of other events such as trend, run, and middle third in connection with out-of-control processes. To do this, you should be able to recognize patterns such as a trend or a run and calculate the probability of their occurrence. Finally, you should also know what the so-called middle third is and how the control limits are calculated. This lesson is divided into 3 parts. First, we will look at a classic value curve in a quality control chart. We then compare this value curve with the associated frequency distribution. This section is for a better understanding of probabilities. After that, let's look at the patterns, trend and run. The appearance of a trend or run indicates an out-of-control process. You will learn to recognize them and understand the mathematical background. Finally, we cover the so-called middle third and periods. Since the occurrence of a middle third event also indicates an out-of-control process, you will also learn to recognize this and to understand the mathematical background. Let's start with the probabilities of control limit violations. On the left side is a table with 50 values. These measured values come from a preliminary production. Below this table is the histogram of these values. This shows the frequency distribution of the measured values with an accumulation at the value 60.11 mm. The curve of these measured values is shown on the right-hand side. A point represents a measurement. To the right of this value curve, we see the histogram of the measured values again. However, aligned in such a way that it corresponds to the distribution of the values in the value curve. In the next image, we replace the histogram with a probability distribution. All 50 measured values were shown before in the histogram. The probability distribution shown here also stands for 100% of all measured values. The area under the curve contains 100% of all values. However, the calculation is based on the relative probability, which is then 1. A quality control chart should now only provide a signal in the case of an unusual event. This means that the probability of a limit violation must be correspondingly small. To do this, you can set the upper control limit and the lower control limit in such a way that the probability that a value lies between these limits is 99 or 99.73%. The range of the 99.73% area is 6 times the standard deviation sigma wide. This probability is represented by the blue area of the probability distribution. The range is thus 1 minus alpha. Alpha is the probability that a value is outside the control limits. Alpha is only 1% or 0.01 in relative terms. This is the area shown in black on the distribution curve. Because of the symmetry, there are alpha half on the left and alpha half on the right. A value outside the limits, as marked here in yellow, is therefore a very rare event and an indication of a process that is no longer stable. A readjustment of the process might be necessary. A value outside the control limits is an exceptional event due to the low probability of less than 1%. Various other patterns can occur in a value curve which also have a probability of occurrence of less than 1%. Such an occurrence would therefore also be an indication of an out-of-control process. One distinguishes here essentially three different patterns. These are the occurrence of a trend, a run, or a middle third. We will go into more detail about all three in the next chapter. Let's start with the trend. A trend, as shown here, is simply a series of consecutively increasing values, but of course also the other way around, a series of consecutive falling values. The question now is, how many values must rise or fall in a row so that the probability of such an event is less than 1%? To approach the solution, let's start with just three values. So the question is, how many ways are there of arranging these three values in a sequential increasing or decreasing fashion? The 6 ways in which three values can be arranged in a sequential increasing or decreasing manner is illustrated here on the left. The first value is symbolized by a circle, the second value by a square, and the third value by a triangle. Only the first two pictures show a first trend. The second and third images show no trend. In order to calculate the probability of a given event, we must first find out how many combinations any number of values can be arranged in. The number of possibilities is calculated mathematically as described below on the left. Two values can be arranged in two different ways, calculated by 1 times 2. Three values can be arranged in 6 different ways, calculated by 1 times 2 times 3. Four values can be arranged in 24 different ways, calculated by 1 times 2 times 3 times 4. In general, mathematical terms, the number of possibilities is calculated by n fractional, where n is the number of values. After we have just calculated the number of possible patterns, we will now calculate the probability that a very specific pattern will occur, such as a series of consecutive increasing values, namely a trend. Let's take a look at the table on the left. The number of values is given in the first column. In our case, this is the number of measured values. The previously calculated possibilities of pattern progressions are in the second column. The probability of a trend calculated from this is in the third column, calculated quite simply by dividing 100% by the number of possible patterns. Next, we expand the table for more values. So, how many values must rise or fall in a row so that the probability of this happening is less than 1%? As you can see from the table, this is the case for the first time with 5 values. So, 5 consecutive rising or falling values indicate a trend, as the probability of such an event is only 0.83%. In practice, however, one does not want to make control charts too sensitive. This would result in too frequent interventions in the process. Therefore, a trend can also be defined as a sequence of 5, 6, 7, or 8 consecutive increasing or decreasing values. A quality control chart should only provide a signal in the case of really exceptional events. Choosing the appropriate sensitivity is then also the task of those responsible for quality and processes. Next, let's take a closer look at the run. A run, as shown here, is simply a series of consecutive values above or below the center line. The probability of such an event occurring should again be less than 1%. Here too, the question arises how many values in a row must be above or below the center line so that the probability of this is less than 1%. To calculate this, we use the multiplication theorem of probabilities. The probability that a value is above or below the center line is 50%. The relative individual probability P1 for the first value is therefore 0.5. The probability is the same for each individual value considered individually. The overall probability P total that a number of consecutive values are above or below the center line is calculated by multiplying the individual probabilities. That is, P to the power of n for any number of values. In this way, the various probabilities for a run are calculated to see for which number of values the probability is less than 1% for the first time. In this table, in the left column, we see the number of consecutive values above or below the center line. As can be seen, with 7 values, the probability is less than 1% for the first time. Thus, 7 values in a row, above or below the center line, indicate a run, and thus a process that is no longer stable. In such a case, an intervention in the process might be necessary. The occurrence of a so-called middle third event is also an indication of an unstable process. Recognizing this pattern or calculating the control limits is not quite as easy as with the trend or run sequences. Next are the explanations and calculations. So, what is the middle third and what does it refer to? As an example, consider the average control chart shown on the right. The middle of the value curve, this is the process location, is at the value 60.1 mm. The values of the samples scatter around the center line. As explained in an earlier lesson, in the United States, the warning limits and control limits are set at multiples of the standard deviation. For the upper control limit, it is 3 times the standard deviation, and for the lower control limit, it is also 3 times the standard deviation. The total width between the control limits is therefore 6 sigma. The middle third is now the middle range with a width of ±1 sigma. In a statistically stable process, 68.27% of all values can be expected in the middle third, which is the ±1 sigma range. With a sample size of 25, as here, this would be 17 values. In order to set an upper limit value, the question must be answered as to how many values above 17 values in the range of ±1 sigma with a sample size of 25 can an out-of-control process be assumed. For a lower limit value, the similar question arises as from how many values below 17 values in the range of ±1 sigma with a range of 25 can an out-of-control process be assumed. As with the trend and the run, the probability of non-interference should again be 99%. Conversely, this means that the probability of a middle third event occurring is less than 1%. The lower limit, here x lower, and the upper limit, here x upper, must be calculated using the binomial distribution. One decisive factor here is the individual probability that a certain number of values x lie in the range of plus minus 1 sigma. So, how likely it is that 0, 1, 2, 3, 4, or 5 and so on values lie in the middle third. This can easily be calculated with Microsoft Excel. The function to be used is called binom.dist, where n is the sample size, here 25. Small p is the percentage of values that are to be expected in the range between plus minus 1 sigma for a statistically stable process. In the table on the right, let's first look at the lowercase b column. This indicates the individual probability that a certain number of x values are in the middle third. As expected, the relative individual probability is highest at 17 values. This is also where the largest blue bar is located. The cumulative probabilities can also be calculated with the same Excel function. These are given in column B in capital letters, starting with 0 for almost 0%, then increasing to 1 for 100%. As a quick reminder, the probability of non-interference should be 99%. The probability of an intervention is therefore less than 1%, as indicated on the left of the diagram. Since there is a lower and an upper control limit, the 1% is divided into 0.5% for the upper value and 0.5% for the lower value, or 0.005 expressed in relative probability. The question for the lower limit is now, at which largest number of values x the condition is met for the first time that the cumulative probability, large B, is less than 0.005. As marked in the table, this is the case for a number of 10 values. There is a 1.03 probability that 11 values are in the middle third. That's more than 0.5%. If there are only 10 values or less in the middle third of a sample size of 25, this is an indication of a statistically unstable and therefore an out-of-control process. An intervention might then be required. Let's see where the upper limit is. The question for the upper limit is now, at which smallest numbers of values x the condition is met for the first time that the cumulative probability, large B, is greater than 0.995. As marked in the table, this is the case for a number of 23 values. There is a 99.44% probability that 22 values are in the middle third. That's less than 99.5%. With a sample size of 25, if 23 values or more are in the middle third, this is an indication of an out-of-control process. An intervention in the process might be required. So, to summarize again briefly, with a sample size of 25, an out-of-control process can be assumed if 10 values or less, or 23 values or more, are in the range between plus minus 1 sigma. An out-of-control process is shown here as an example in which 23 values are in the middle third. And here is an out-of-control process shown where 10 values are in the middle third. Finally, a few comments on repeating patterns in value progressions, so-called periods. Under normal circumstances, measured values are expected to be randomly distributed. Such a pattern of values is shown here in the diagram for the first 25 values. A repeating pattern can be seen for the next 25 values. The two waves are shown here as an example. Other patterns are of course also possible. Periods, this means repeating patterns, should also be examined, as they can also be an indication of a statistically unstable process. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 5 most important key messages. We tried to identify patterns whose occurrences have a probability of less than 1% and which thereby indicate an out-of-control process. A trend is a sequence of 5 to 8 consecutive rising or falling values. 7 values in a row above or below the center line indicate a run. The non-interference probability should be 99%. The middle third has a width of ±1 sigma. If there are more or fewer values in this range than expected, it can be assumed that the process has become unstable. Recurring patterns, like periods, also indicate an unstable process. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!